Welcome to the last talk of the first day. So the last talk is by Max Hopkins, and he's going to tell us about integrality gaps for 3-lin and relation to high-dimensional expanders. So take it away, Max.
Thanks, Dor. Thanks so much, everyone, for coming to the last session of the day. Hopefully, you can stay awake for the next hour, but if not, no worries. We know how it is. You and the friend. So I'll be talking about this work on explicit SOS lower bounds or integrality gaps within the sum of squares hierarchy based on some new notions of high-dimensional expanders. This is joint work with Ting-Chun Lin or David, who's probably here somewhere. Yeah, there he is. Thanks. Okay, so I want to start with just some high-level background on what sum of squares is. We'll keep this relatively high level, and then I'll go into a specific problem, 3 XOR, and we'll be a little bit more detailed. But really, even though there's SOS in the title of this talk, you really won't need to know anything about SOS for this talk. So just briefly, at a high level, the sum of squares SDP hierarchy is essentially a very powerful framework for constrained polynomial optimization problems. So this is a framework for polynomial optimization. And it's particularly powerful for solving computer scientists' favorite problems, constraint satisfaction problems. And we'll talk about a specific one in a second. Many classical CSP algorithms turned out to be captured by, say, constantly many what are called rounds of the SOS hierarchy. And we actually know from beautiful work of Grigoriev that under the unique games conjecture, that the sum of squares hierarchy optimally approximates the value for all CSPs. So this is a very, very powerful framework. Roughly speaking, you can sort of think of this SDP hierarchy as a computational model, like a restricted model of computation that's divided up into levels. If I have an n variable, say CSP, it'll have levels ranging from 1 to n, so divided into levels 1 through n. And roughly speaking, I just sort of want to mention two things. The teeth level of the hierarchy basically looks at sort of ensembles of t variables at once, along with some low degree consistency constraints. So sort of looks at, very informally, sets of t variables at once. And critically, it runs in time like n to the O of t. So if you have a constant round thing, it runs in polynomial time. So runtime n to the O of t. On the other hand, when you reach the top of the hierarchy at level n, we can see all the variables, and you can essentially like brute force over the solutions. We can level n will solve any CSP. Okay, that was sort of the only high-level things I wanted to say about sum of squares. And now I want to focus on a specific constraint satisfaction problem that I imagine everybody in the room is familiar with, which is just 3 XOR, one of the most classical constraint satisfaction problems we study in complexity. So what is 3 XOR? I probably don't need to write this out, but I will. So an instance of 3 XOR on n variables, this will consist of a set of variables xi, where I ranges from 1 through n, and a family of clauses. And we'll write that there are m clauses. And for the sake of this talk, and actually the paper that I'll be talking about, I'll note that m should always be thought of as linear in n. There'll be like 100 n clauses or 1,000 n clauses or something like that. And okay, what's the form of these clauses? They're just linear equations with 3 variables, right? So the clause Cj is going to be something like xj1 plus xj2 plus xj3. And then there's some literal that I set them equal to. They're either equal to 0 or to 1. So they're equal to some beta j in F2. Okay, so that's an instance of 3 XOR. What are we interested in? Well, we're interested in calculating the instance's value, which is the maximum number of constraints that I can satisfy at once by some F2 assignment to the variables. Right, so the value, right, value of in, this is, again, the maximum over assignments of x to the variables of the value, which I'll just write out explicitly here so that it matches the SDP over there. You can compute that the value of a particular x is the sum over the clauses of just making sure that the beta j is equal to the sign of -1 to the beta j is equal to the sign of -1 to this clause. Okay, so there's an explicit formula for the value. Notice that if I'm doing this over F2, because eventually when we move to talking about lower bounds, it'll be useful to have things sort of additive notation. If I switch to +(-1) to the n, these would be multiplying, and this would be like a polynomial optimization problem, right, which is where SOS comes into the picture. So let's actually move over very briefly to the level T sum of squares SCP relaxation. Maybe I'll wait for the screen to adjust so everyone can see this. Okay, maybe not. I don't want to actually say that much about this relaxation. For every subset of variables of size up to d, I introduce a new sort of vector valued relaxation for. I'm maximizing some relaxation of exactly this value, and I'll call sort of the actual maximum of this program. I'll denote as the SDP value of in. Maybe I'll write a t here if I'm corresponding to some number of levels. And there are constraints here that correspond to some consistency constraints between the variables and some Booleanity constraints. But again, it's not that important that we understand exactly what this program is. Really the point.
What is the set on the right-hand side of the maximize?
What is the set on, what is this?
US,
US are the variables. So
farther to the right.
This? Farther to the end.
Farther to the right.
Farther to the right. This.
That.
Empty set. This is the empty set.
Okay.
So this is supposed to stand for like the ones, standard thing all ones. Okay. Yeah, okay, sorry. Okay, really the only point that I want to make about this is that it's a relaxation in the sense that the STP value lies somewhere between the true value of the instance, and this you get just by sort of plugging in the relaxation of actual solutions, and 1, because of how I've normalized things, this will always cap out at 1. Okay, so what was the point of this? Well, now I'm going to define what it means to be hard or to have a lower bound against sum of squares. And so we'll say that a family, so typically when we talk about lower bounds and complexity, we like to talk about not specific instances, right? You could hard code an algorithm for specific instance, but an infinite family of instances. So we'll have some sort of infinite family of 3 XOR instances with n scaling to infinity. And we'll say they're hard for sum of squares. In particular, actually something more, we'll ask that they are hard to approximate if there exists a constant mu in 0, 1, such that for all n, or for all of these instances, we have the following 2 properties. First is usually referred to as soundness, and this is just going to say that the instances are very far from being, the true value of the instances is small. It's far from being satisfied, that the value of in should be less than or equal to mu. So there's some number that's bounded away from 1 with respect to the size of n, 99% or something like that, and I can never satisfy more than 99% of the clauses at once. So these are highly unsatisfiable instances, and yet completeness will mean that nevertheless the SDP value will be as poor as possible. So maybe we'll say hardness against T levels of SOS would mean that the Tth SDP relaxation has value 1. So sum of squares cannot determine, cannot tell that this instance is actually very unsatisfiable, and thinks that it is that there is a fully satisfying solution. And notice that, why do I say hardness of approximation here? Well, you could ask for something a little bit less, which is like, maybe I just want to ask that this is less than 1 and not bounded away. This might be something like 1 minus 1 over n or something that scales with n. And this doesn't give a lower bound against approximation, right? Because the value is 1 minus 1 over n, and 1 will be within some, any constant of each other for large enough n. So I actually need to be like bounded away from 1 to give it an approximability result, which will be what the focus of this talk is. So here's sort of the main question for this talk, which is what CSPs, and in particular, we'll look at what instances of 3 XOR are hard for sum of squares. there is a very classical answer to this question. And it's the first thing that I want to talk about. So some background on what we know about this. And this is a result that was originally proved by Grigoriev in '99, and then it was rediscovered by Schoenebeck in 2008. And it's a beautiful theorem. So Grigoriev, '99, Schoenebeck, '08. And it says, first I'll just say informally, it says that random instances, random families of 3 XOR are basically optimally hard. So random XOR are hard. And let me be a little bit more explicit. So if we have, some n variables, and we'll pick, say, m random clauses. I'll be a little bit more specific about exactly what it means to pick a random clause in a bit, but it's just what you think. Then the following two properties hold with high probability over these choices. The soundness is near optimal. The value of in will be less than half plus epsilon, where epsilon is really something that scales with like the constant on this on the number of clauses. I'm not going to go too much into the relationship here, but notice that this is optimal because in a 3 XOR instance, if I just pick a random assignment, I'm going to satisfy half the equations in expectation. So I'm clearly not going to do better than half. So half plus epsilon is like the optimal thing that you can hope for. And it will have completeness. So the SDP value of in will be equal to 1 all the way up to O of n levels of SOS. So this is a very, very strong, remember that n levels of SOS solves everything. So this is an extremely strong lower bound. It says all the way up to some, n over 5 or some constant linearly many levels. Random instances trick sum of squares. It thinks that the value is 1, even though it's sort of optimally far. Okay, this is a beautiful theorem. And in building up to what the main thing we'll talk about, we'll actually see the proof of this or a sketch of it. And this generated a really long line of work on understanding more generally the hardness of random constraint satisfaction problems beyond 3 XOR, other types of structures, independent set, combinatorial structures. But something that had remained, as far as I know, pretty much completely open until a year or two ago, is whether the randomness in all of these constructions was necessary. In particular, well, we already know from the title, but the main question that we'll actually discuss is sort of whether this result can be de-randomized, or in particular, are there explicit families? Are there instances that are constructible in polynomial time that are hard for SOS? Okay, so maybe just a comment, why, if we have sort of this whole landscape of random things, why is it so hard to get something for the explicit case? Well, first I'll mention that actually, if you want something like, not for the approximation regime, it's actually not that hard. In fact, even maybe before the random case, something like this was known for certain parity systems. But the reason in general this result is so much harder, or it seems to be, is that deterministic instances, things that you can construct in polynomial time, they have short witnesses. They have short proofs of unsatisfiability. And you have to show that sum of squares can't capture these proofs. And this is a different type of statement than showing that sum of squares can't capture like a Chernoff bound, which is how you prove often these sort of basic random things. Okay. So a couple years ago, maybe at end of 2020 or 2021, there was a really beautiful result towards this direction of Dinur, Filmus, Harsha, and Tulsiani, who showed how to build the first explicit hard instances against sum of squares. And let me sort of show exactly what they proved. And to me, this was really cool because they did it using high-dimensional expanders, which is very exciting. So here's sort of what they proved. This is Dinur, Filmus, Harsha, Tulsiani. This is in ITS 2021. And they proved the following: that there exists an explicit infinite family of 3 XOR instances I of n. And I'll note, I won't say exactly what this means for the moment, but we'll sort of see a variant of it later in the talk, that in some sense sit on a family of high dimensional expanders. So sort of define on top of what are called the Ramanujan complexes, which is some sort of famous family of high dimensional expanders that satisfy the following guarantees, which we'll sort of compare up here to what we get for random instances. So the soundness is, I didn't recover half plus epsilon, but the value of I of n, I'm going to cheat a little bit here. I'm just going to make up some constant. It's some constant that's not 1. I'm not totally sure what the right constant is, but there's some mu that it's bound, the value is bounded away from 1. And then the completeness, they show that the SDP value of I of n is 1 up to root log n levels of SOS. Okay, so let's compare this to the Grigoriev results. There's sort of 2 main points of comparison. The first is the soundness value of being half plus epsilon, remember we said was optimal, versus sort of 99%. And this one I'll mention is not such a big deal, because it turns out that from much previous work of Tulsiani in 2009, you can sort of use PCP reductions to move from this instance to something with half plus epsilon, albeit maybe you lose like a little bit in the completeness, or you can actually not lose in completeness and lose in levels. But this is not such a huge issue. We sort of know how to reduce to instances that have optimal gaps. This seems to be the bigger issue. This had to do with some properties of the Ramanujan complex that was very unclear how to improve on. And it doesn't, approaching, it's not even polynomial, much less close to this linear hardness. And in fact, there was an interesting observation from Kevin Pratt, who is maybe also here, who observed that you can actually get instances verse about log n levels by some sort of brute force argument over small random instances. So that was a little disappointing, because I really like this sort of application of high dimensional expanders. And I really wanted this to be the right direction. And thankfully last year in this joint work with David Lin, we sort of fixed the version of the results, and we showed that this approach, we follow very closely sort of this approach, HDX-based approach of Dinur, Filmus, Harsha, and Tulsiani. And we show that this is indeed, if not the right approach, a right approach. And so we prove sort of the following theorem, which I'll redo in red. There are only 2 changes. The Ramanujan complexes are replaced with an object that I will define later in the talk called the small set high dimensional expander. These are things that ended up coming out of quantum codes. If we have time at the end, I'll talk about this. And this gets replaced with indeed linear levels matching Grigoriev's result. Yeah, and okay, maybe I'll mention that also, if you wanted hard explicit instances for things that are not XOR, again, you can run these things through PCP reductions to get hardness for other instances. So this sort of gives a whole landscape of explicit hard CSPs for some O squares. Okay, maybe any questions before? So now I've stated the main results. My goal in the rest of this talk, yeah, Anthony.
Yeah, so you said there's some trade-off that you can tweak parameters to get some sort of trade-offs here.
Yeah.
Is there some way to tweak this theorem to push close to this like 1/2 bound for sound?
Yeah. So I mean, you can use PCP reductions to get to half plus epsilon. Like if you use the long code based like noise reductions, then you lose something in the completeness. Per Oshman pointed out that if you use the Hadamard code in parallel repetition, then you can maintain perfect completeness, but you end up, I think, with something like n to the epsilon levels. So actually achieving both of these simultaneously is an open problem. And also, actually, I'll say just, I mean, this is something that Dor brought up to me earlier, just sort of directly achieving 1/2 plus epsilon without going through these PCP reductions and having something that like sits on a complex would itself be very interesting. And in some sense, this might also correspond to like a good distance quantum code. So it's sort of an independently interesting problem in other areas. Okay, yeah, good question. Okay, so my goal here I want to try to convince you that this notion of high-dimensional expansion actually does arise pretty naturally when you try to solve this problem. And so I'm not going to start by, this is like a topological notion of HDX, and I've seen many people give talks on topological HDX. And when it's to a CS audience, half the people, eyes glaze over. So we're gonna skip that step, and we're gonna try to see how this arises within this actual problem framework. And then hopefully, if we have time, I'll try to show you how you actually get explicit constructions of these objects. Though I sort of had the feeling I'll briefly sketch this at the end. Okay, so that's the plan for the rest of the talk. So the first thing that I want to do to show why this type of structure arises is to go back to this original result of Grigoriev and Schoenebeck. In particular, we'll follow sort of the proof within Schoenebeck. And the key thing that we'll observe here is that expansion already played like a big role in this result. So in particular, to understand this, it'll be useful to move to the graph view of 3 XOR. So we can always draw graph view. So we can always draw an instance of 3 XOR in the following way. We'll have a constraint graph. And I'm now realizing maybe I shouldn't have erased the definition of 3 XOR. This was just things with these clauses like xj1 plus xj2 plus xj3 equals beta j, right? So this left side is going to be given by the constraint structure of a graph. In particular, so we'll have a bipartite graph where on one side we have the variables. This is x1 through xn, and on the right side we have the clauses. So like Cj, and then following this equation, we just connect Cj to the variables that are in the clause, right? This goes to xj1, xj2, xj3. And then, okay, we're not quite done, right? Because we've specified this part of the picture, but we also need to specify sort of the right-hand side of the equation, which I'll call the target function. So we need a constraint graph plus target function. And this will just be a labeling of the right-hand side of this graph, right? A 0, 1 labeling, and I'll write it as beta in f2 to the c. So this is just something that's isomorphic to f2 to the m. There are m clauses, but you can think about either of this as like a subset of the right-hand side, or a labeling, or a function. And I'll probably move between them when talking about things because it's useful to think of them in different ways. Okay, and so now what is the random instance that showed up in this result? Well, I'll fix the number of clauses C and the variables, and then I'll just pick a random bipartite graph, right? For every vertex here, I'll just pick 3 random vertices and draw edges to them, and then I'll pick a uniformly random target function from f to the C, and this is the claimed result that it satisfies this type of structure. So you can see that sort of the randomness comes in 2 parts, right? There's a randomness over this constraint graph, and then there's the randomness over beta. And the first thing that I want to show you is that the randomness in the constraint graph, this is actually not necessary. This can be de-randomized easily. In particular, what you actually need is that this is an expander. And this is where we're going to see expansion first enter the picture, and eventually the notion of expansion that's useful here is going to get generalized to some high dimensional version. So, okay, exactly what notion of expansion do I need this to define to satisfy? Well, to do this, I need to define what's called the boundary operator. So if you remember back from the boot camp lectures of Arit, everything that I'm doing here is going to correspond to the boundary and co-boundary setup that she defined. But if not, I'll do it again here. So the boundary operator, we'll write as partial. This is just the adjacency matrix, the bipartite adjacency matrix of this graph going from clauses to variables, but we'll view its action over F2. We'll view it as acting on F2, and in particular, so maybe I'll define this here, the boundary operator delta. So this maps functions from F2 to the C, the functions or sets on F2 to the C to sets on variables. And if I look, if I have some function f on this side, then delta f of x. So what's the value of this delta f of x is over here. What's the value? It's just going to be the mod 2 sum over the neighbors on the right-hand side. Right? This is the sum mod 2 over the y neighboring x of f of y. So in this case, it's the sum over clauses that it's contained in. And this value is 1 exactly when the variable appears in an odd number of clauses, and 0 when it appears in an even number of clauses. This seems like a little bit of a weird notion. We'll see why it makes sense within this context of sum of squares. But I'll maybe try to give a little bit of motivation for the moment, which is when I look at delta f, this corresponds to the set of variables that appears an odd number of times over here in the clauses. Equivalently, I can think of this as if I sum the variables, if I sum up all the clauses, the left side of all the clauses, delta f is exactly the set of variables that live through this process, that don't cancel. So the notion of boundary, of expansion that we're going to use is basically going to say if I have some, reasonably, not too huge, but reasonable set of clauses, when I sum them all up, there should be a lot of variables that still exist in this sum. There shouldn't be a lot of cancellations. And that's going to allow us to build, over here, we sort of said that sum of squares only gets to look at these sort of small portions. And if I can prove that, to find a contradiction, I have to sum up many things and see many variables at once. That's going to lead to a lower bound against SOS. That's sort of why this is going to be useful. So let me actually formally define boundary expansion. So we'll say this graph G is an alpha some constant, alpha small set, boundary expander. If for all functions or sets on the right side, such that they're linear size, that have, this is just number of ones that's in the function, is at most an alpha fraction of the clauses, then I want this sort of notion of boundary to be large, right? I want sort of the following isoperimetric inequality. I want the boundary of f to be at least alpha times the size of f. So basically, the size of the boundary should scale with the size of the function, as long as I'm not too large. Okay, so that's the formal definition.
These are called boundary expanders, not co-boundary expanders.
Yeah, so this direction is boundary. This direction, which we will see later, is co-boundary. And if we had this property in the other direction, it would be a co-boundary expander. And the important thing is going to end up showing some complexes that are simultaneously satisfy both of them, it turns out. But that's sort of not obvious at the start. Okay, so these are boundary expanders. So I want to show you how boundary expansion actually implies completeness against SOS, since this is what we're going to generalize to high-dimensional boundary expansion. So the following proof, I guess, formally appears in Schoenebeck. It's probably not all that different from what was originally done by Grigoriev. But Schoenebeck proved that, if the constraint graph of your instance, which I'll just write as G, is I'm going to ignore sort of whatever this constant is. For some constant, it's a boundary expander. This implies completeness, SDP value 1 versus up to O of n levels of SOS. And notice that this is this version is completely independent of the target function. It doesn't matter what target function I pick. We can prove the SDP value is going to be 1 no matter what. Okay, so I want to sort of sketch this result to give you this intuition for why this is relevant, and then eventually why the notion of high-dimensional expansion we introduce is sort of a natural way to go. So the proof, luckily for us, doesn't go through sum of squares. it goes through proving a refutation lower bound against the XOR resolution system. So it goes through, it's called the XOR resolution system. And this is a very simple proof system, which basically says, we have some axioms that are given by linear equations, and I can derive things by just summing the linear equations. That's the whole thing. So I'll have some axioms that correspond to linear equations. And for us, these axioms are just the clauses. Maybe I should have said J. These are just the clauses in our XOR instance. And then, given two axioms, we can derive the equation of their sum. So given, or really just given n equals beta I, we can derive Li plus Lj is equal to beta I plus beta j. Remember, these are like variables, and these are F2 values. Okay, what's the point of this? Well, we're going to look at how, how do I use this system to prove that my instance is unsatisfiable, to find a contradiction. Right? So we'll use something called a refutation. So very roughly, a refutation is just a way to add up the axioms together that derive 0 equals 1. In other words, on the left-hand side, I want to add them up in a way such that all the variables cancel. I find a cycle. Whereas on the other hand, things are going to sum to 1, and I get this contradiction of 0 equals 1. Clearly, the instance can't be satisfiable. So a little bit more formally, a refutation will consist of a DAG, which has leaf nodes that are labeled by axioms. So I'll maybe draw a picture over here, I guess. So here we'll have x1 plus x3 plus x5 is equal to 0, and here we'll have x1 plus x3 plus x7 is equal to 1. And then the inner nodes of the tree, so the internal nodes, have two incoming children, and they're just labeled by the sum of the equations in their children. So in this case, this ends up being like x5 plus x7 is equal to 1, just summing these two equations. So notice that things sort of can cancel when I move throughout this tree, and this is the behavior I want to avoid. So internal nodes are labeled by the sum of their children, which I'll just write as like L of child left plus L of child right equals beta child left plus, be a little informal, sorry, beta of child right. And then finally, we'll have sort of a bunch of these, and eventually these will come up to the root node, which is supposed to derive the contradiction 0 equals 1. So again, it's just a formal way of summing up these equations that hits this contradiction. So root is 0 equals 1. And what's the complexity of a refutation? Well, it's going to be the maximum number of variables that appear in any of these internal nodes. So the width of a refutation is the max number of variables that appear over the nodes. And the refutation complexity of an instance, a 3 XOR instance, is the minimum width over all possible different refutations. So the refutation width of IN is the minimum width over refutations. So if I have refutation complexity or refutation width 10, it means that any way that I can derive this solution 0 equals 1, I have to go through 10 levels. And Schoenbeck proved the following theorem, which is what's going to allow us to ignore what's on this board over here. I shouldn't write here because of this. He proved that if the refutation width of IN is greater than or equal to 2 times T, then this implies completeness versus T levels of SOS. So if we want to prove a linear lower bound on levels for SOS, we can do this by proving that in any refutation, I must somewhere hit a linear number of variables in this tree. Yeah. I don't think so, but I'm not. Dinur, do you know if the converse of this is true?
I mean, SOS can do the XOR refutation, right?
Yeah. So if
you right, so I mean, if you can fool XOR refutation, you can fool SOS, and if you can't fool XOR refutation, then you certainly can't fool SOS.
right, but an SOS lower bound doesn't necessarily imply a refutation lower bound, right? What you're saying.
Oh.
An SOS lower bound shouldn't. That's what I thought your question was. Sorry. Yeah. Okay. I don't think it does. Yeah.
Refutation is stronger than SOS.
Yeah, refutation should be stronger. Yeah, that's yeah. But I don't know an explicit example to give of this, but I think it should be. Okay, so we've reduced the problem to showing large refutation width, and now I want to show you what boundary expansion, which thankfully I didn't erase, has to do with this. And I promise eventually we'll get to high dimensional expansion, but it'll just be some modification of this argument, which is why I'm going through it. Okay, now I'm going to erase this. Okay, so the idea, actually, essentially, this was proved earlier by Ben Tseitin and Vigdersen, and this is like an adjustment to 3 XOR. I think they did it for SAT. And it's a beautiful argument. Basically, the idea is to track through this refutation the number of clauses that, here we're tracking sort of the number of variables. That's what we want to prove a bound on. What's much easier is to track the number of clauses that appears in each internal node. And I can do this by defining a function with respect to each of these nodes that corresponds over to this picture, a function on the right-hand side of clauses. That's just a 1 if that clause is got summed into that node and 0 otherwise. And okay, formally I do this by, I have this function hv for each node in here, where h on the leaves is just equal to whatever the indicator function of whatever clause it was. So if this was clause 2, this would be the indicator vector of clause 2. So I put all these indicators on the bottom of the tree, and then I define hv just by summing these functions over the children, right? So this is just equal to hv of like the left child plus hv of the right child, and hopefully you can see what this is tracking is exactly like which clauses are appearing in the internal nodes. And this is some function on the right. And how are we going to use boundary expansion? Well, what boundary expansion says is that, small set boundary expansion, it basically says if I can find sort of any node in here that has somewhere between, say, an alpha over 2 fraction of the clauses and an alpha fraction of the clauses. So if I can find something where the size of HV lies in here, then boundary expansion exactly tells me that this can't cancel too much from the left side, and there have to be a linear number of variables that appear, right? In particular, this forces the size of delta HV, which is exactly the number of variables that appear in this equation. This has to be greater than alpha times HV, which is greater than or equal to alpha squared over 2 times n. And this would give us our width lower bounds and bound on SOS. Okay, so how do you prove this? Well, now we've sort of reduced to just finding some inner node that has many clauses in it, has this many clauses. And the argument here is very simple. So we'll define a potential function over the nodes of the tree, which is just equal to this size of number of clauses that we want to track. And we'll note 3 things. The first thing we'll note is that the root has potential kappa of root is greater than alpha m. And roughly the reason for this is that this is sums to a cycle. And moreover, it's a non-zero cycle because I can't have summed 0 things and gotten 1. But boundary expansion promises you right? If my thing is of size less than alpha m, then the boundary will be something. It'll be greater than 0. So actually, this type of boundary expansion it's much stronger than this is just something about saying there are no small cycles, non-trivial cycles. So the root has large potential. Second, okay, clearly the leaves have potential 1, right? These are each indicators. So the leaves have potential 1. And moreover, when I add the clauses from here and add the clauses from here, this potential function is subadditive. I can't add 5 clauses and 5 clauses and end up with 11 clauses, right? It's this satisfies that kappa of v is less than or equal to kappa of v, the 2 children. And okay, I claim that it's not hard to see that if I start at 1 and I have to end at greater than alpha m, somewhere in the tree, I'm adding 2 things, I have to pass through alpha m over 2. But if I never did, I'd never be able to reach alpha m, and that completes the result. So this is this very nice argument of Tseitin and Wigderson. Okay, so this sort of completes the proof of completeness. And now at least we know that if we want to de-randomize things, this is not really the hard part, because we have constructions of boundary expanders or even like unique neighbor expanders, which imply boundary expansion, because unique neighbor is like I hit many things exactly 1 time, which is an odd number. Yeah. Right, but we don't need it for this one because it's XOR structure. Yeah. Okay, so clearly the issue, the hardness must be lying in this target function. Right, so if I now wanted to complete the proof of Grigoriev or Schreinebeck, now it's really easy. So how do we find sort of unsatisfiable beta? Remember, these are the target function. This is this labeling for the right-hand side. Okay, so this original solution was to choose it randomly. And why does this work? Well, if I have any fixed solution, this generates some number of values over on the right-hand side. And if I pick them randomly, on an expectation, half of them will be correct. And moreover, by like a Chernoff bound, and if I take enough clauses, this will be true with extraordinarily high probability. And then I can union bound over all the possible solutions. Okay, so Schreinebeck proved. So randomly works. I'm gonna get this half plus epsilon. So how do we do this explicitly? Is there anything sort of, is there any reasonable way to try to get something that's unsatisfiable? Well, actually,
how do you get the 3 XOR instance?
3 XOR instance is defined by the constraint graph, and then some labeling on the like 0, 1 labeling on the constraints. Right. This tells you the variable structure, and then I pick some function beta, and the variable structure gets set equal to beta. I'm not sure I'm answering your questions. So this is the value of beta on CJ. Okay, good. So how do we find a beta explicitly that's unsatisfiable? Well, I claim if all you want to do is find something that's unsatisfiable, actually, this is not that hard. If you don't want to get hardness of approximation, I can do this using linear algebra. In particular, earlier I drew this coboundary operator, which is just the transpose of this operator, the boundary operator. And what is delta 0? So we'll define the coboundary operator. So again, this is just the adjacency matrix here acting over F2, but now moving in this direction. So delta 0 maps F2 to the V, to F2 to the C, and delta 0. Now I'm applying to like a function over V, or you can think of it as an assignment. And the value of this on something on the right is again just the sum over like Z adjacent to Y of f of Z. Okay, maybe this was a needlessly abstract way to write it. If I have some assignment over here and I want to ask what's the value of delta X on CJ, it's just the sum, it's exactly this sum, right? It's the mod 2 sum over the variables that are included in J. So it's just the clause value of the instance. So in particular, I claim that this implies the following, that the space of satisfiable solutions, the space of beta that lead to satisfiable instances, well, what are these? this is exactly the space of things that map from some assignment to the variables, right? This is exactly where I pick some assignment here, and I see what values they give on the clauses, and that's exactly the set of beta that's satisfiable. So in particular, this is exactly the image of delta 0, which are usually called the coboundaries, written as B1. I should have noted that the image of this are usually called boundaries and are denoted by B lowercase 1. Okay, so this suggests sort of a natural strategy. Using linear algebra, like Gaussian elimination or something, I can just find, pick beta in, sorry, that should be F2 to the C without B1. And I can do this explicitly, right? I can find some beta that's not in this image, just like list the basis vectors of this and check. And this equation promises me that this leads to an unsatisfiable instance. The problem is that the value of the corresponding instance, if I pick some beta, it might be like 1 minus 1 over m or something. I might just satisfy everything except one clause, and I want to get this like half plus epsilon or 99%, right? So this is really where the difficulty comes in. Okay, let me erase this. So here's sort of a very nice idea that is from this work of Dinur, Filmus, Harsha, and Tulsiani. They say, okay, why look over? What's really the problem here? The problem here is that F2 to the C contained functions that were really close to the boundary. And I somehow only want to look over things that are far away from the boundary, right? Intuitively, things that are far from the boundary should be far from satisfiable. And I'll maybe write that in equation form soon. And so, you can kind of ask the following question. Can we find a subspace that sits somewhere between B1 and F2 to the C? So can we find some subspace that I'll call Z1, because it'll eventually will be cocycles, that sits between B1 and the entire space, that has the following property. If I look over all of the functions in this subspace Z1 that are not in B1, so if I look at the minimum over functions in Z1 without B1 of the distance of F from B1, then I want this value to be linear. I want everything to be linearly far away from stuff in this satisfiable space. Is it possible to find something like this? And let me simplify this a little bit, right? Because this is a subspace that I'm picking. What is this distance? This distance is the minimum over things in B1 of the weight of F plus B, but B1 is part of Z1, so I'm just, and this is a subspace, so F plus B is actually in Z. So this minimum equation here is really just the minimum Hamming weight of anything in this set. So I can replace this with asking if the minimum size of F is greater than or equal to alpha times m. And if you're a coding theorist, there should be like alarm bells going off in your mind right now, because this is like asking about the distance of the code Z1 mod B1. And this will allow us to use coding theory and connections with coding theory to solve this problem. Okay. What does this have to do with high dimensional expansion or expansion at all? We finally reached sort of the point where I can discuss this. I'm going to redraw this diagram over here. Sorry, maybe I should actually explicitly say that if you can actually find this, then a claim that's easy to show is that for any f in here, if I pick this as my target function, the value of I beta will be less than or equal to 1 minus alpha. It's an easy calculation to show this. It's just a robust version of that earlier statement. It says if something's far from the boundary, then it's far from satisfiable. Okay, so we would be, if we could find this explicit subspace on an instance that's a boundary expander, we'd be done. It turns out there's a problem with this. And to show the problem, I want to sort of write this up as a higher dimensional picture. Okay, so we still have the vertices. We have the clauses. And now here's like a totally generic way to talk about defining this Z1, but over in a graph picture. I can add a third layer to this structure that essentially corresponds to the parity checks, or like the generators of the orthogonal subspace of Z1 that defines this space. So remember we had like the standard coboundary. Here these were like connected to this clause Cj was connected to maybe x3 plus x7 plus x10 or something. And now when I define this subspace, I'll call this P for like parity checks. The way that I'm defining it is when I pick beta, remember the beta that I'm picking is some labeling, some function on C, I'm going to enforce that when I sum over the values, over the neighbors of each parity check, that I get 0. This is an equivalent way of expressing this type of subspace. And okay, so in this diagram, somehow, sorry, I guess I should say that when I do this, this is again just the adjacency operator running in this direction. And what is Z1? In this picture, Z1 is the kernel of this operator delta 1, right? So this is basically the parity check matrix corresponding to this subspace, everything that's in the kernel of this operator. So we just want something that Z1 has this minimum distance property. But I'll mention that when you're in a complex, these are called cocycles. And this property of having everything being of weight greater than or equal to alpha m is called cosystolic distance. So this is that property over there was, I'll just say, having good cosystolic distance. Okay, so what's the point? I want to sort of build some complex like this that simultaneously has good cosystolic distance, so sort of good properties in this direction, and I want it to be a boundary expander, right? I want to get completeness. I want this result of Schoenebeck. So I want to show that in this direction, at least from C to V, small sets in here expand to many things here. But this is a problem because in how I define this by picking B1 within Z1, what I've implicitly done, okay, so this is the kernel of delta 1, right? And this was the image of the first operator. So the fact that B1 is in Z1 means when I map something from here to here, it's in the kernel, which means when I map it again, I get 0, which means this whole complex necessarily satisfies the relation delta 0, delta 1 equals 0, which is what's called being a chain complex. It is used in, studied heavily in algebraic topology in lots of areas, and it's has very useful things we can draw on. But here it's a little bit problematic because if delta 1, delta 0 is 0, then when I look at the boundary operators, which are its transposes, this means that delta delta is also 0. Why is that a problem? Because look at this parity check that I've drawn. I claim that when I have this structure, this means that there is going to be a small non-expanding set in this graph, no matter what I do. Because when I look at just applying delta to the indicator of this parity check, I get like a set of size 4 here, and because it has to be it's forced to be in the kernel, that maps to nothing over here. It gives a short cycle. So this graph, Schoenebeck's result is going to break down because this graph is not because of this high dimensional component, it cannot be a small set expander. Okay, so we've seen this occur in maybe 50% of the talks at the boot camp and the workshop so far. We had some notion of small set expansion or expansion. We moved to some different object like HDX or the Grossman or something like this. And these objects had sort of these canonical local bad sets that didn't expand. And what did we prove? Well, every time we found some way to show that as long as you're not correlated with one of these functions, as long as I'm far from this set of canonical bad elements, then I will maintain this type of isoperimetry. I'll maintain this expansion. And this is what I call small set high dimensional expansion, or at least in the boundary direction. So we'll define a small, alpha small set boundary HDX corresponds to one of these sort of 3-term chains where, let's just mimic the definition that was going on over here for all functions in this middle layer, F2 to the C, that have size are less than an alpha fraction of the graph, then we want that the boundary, the size of the boundary. Oh, okay, I wanted to write F here, but I just showed you that that can't possibly be true. Yeah.
This counterexample holds only if the degree of from
Yeah,
P
that's
is
good. If these are all high degree.
all high degree.
So it's possible you might be able to get this result to work if you pick something high degree.
Okay.
Yeah, I was thinking about this last night. I don't know how to construct such a thing, but if you could, I think it would get you an SOS power bound. In fact, there are other things that maybe, like you could also try to find Z1 that's not in V1, and there are some reasons why, or that doesn't have this containment, and then you also wouldn't have this. But this has some other reasons you might not want to do it. I didn't want to get too much into it. So yeah, very good point. So the constructions that we have, they'll come from like LDPC codes, meaning that these will actually be some constant. And so they will truly give you non-expanding sets. Okay, let me finally get to the payoff because I'm pretty close to out of time. Which is that instead of the weight of F, which is what we would have had here in expansion, now that we have this extra dimension and we have these canonical non-expanding functions, which let's write these are the canonical non-expanding things are the image of this map. These are usually called the boundaries. I think I did the wrong definition over here. It should have been B0. Sorry about that. We want that this is alpha times the distance of F to the boundaries. And so this is sort of the best possible thing you could hope for, because the boundaries are these canonical families of non-expanding sets. And I'll mention if you want to write this as sort of a more classical, look something like this as a classical isoperimetric inequality, we can do the thing that of like defining global functions, or usually here they're called minimal. So if F is small and it's called minimal, which means that I can't add a boundary to it and reduce the weight, then I would recover actually this isoperimetric inequality. And I don't have time, and I wasn't going to go through it anyway. Did I erase I did erase the proof of oh no, it's okay. No, it's not over here. So we saw this proof for the refutation proof where we used the potential function. We used this as the potential function, right? So we looked at we had this tree, and we looked at sort of the number of clauses that was maintained in each thing. I'm just going to repeat this proof, or I'm not, but you can, and in fact is done in this earlier work of Dinur, Filmus, Harsha, and Tulsiani. They did it in a special case of the Ramanujan complex and used a much weaker isoperimetric inequality of Gromov, but the same ideas are there. You just replace the potential function now with this distance. And you have to be a little bit careful, but the whole proof goes through. So, just replacing sort of standard isoperimetry with this isoperimetry for minimal functions or high dimensional version of the isoperimetry gives you the completeness result back. So I have 1 or 2 minutes. This is all well and good, but this is useless unless I can actually build complexes that satisfy these two notions. So this is the final theorem, which I was hoping to actually say something about the proof, but I probably won't have time. Which is, indeed, these objects exist. And in fact, something even stronger exists. So there exists explicit infinite family of, I'll call these complexes like capital X or something. So some infinite family of these explicit complexes such that for all functions in the middle, people probably can't see this, can they? Yeah, okay. Sorry, NF2 to the C. The first thing is that we have this guarantee, right? We have boundary expansion, distance of F from B1. And moreover, the constructions are symmetric. So we actually have it fully in the other direction as well. The 2, it also has what I'd call co-boundary expansion in the other direction. I'll finish writing this distance of F. Oh, I forgot to write that. Yes. Yeah, so actually, by the way, this is just like a small set version of the classical notions of boundary and co-boundary expansion. I mean, it's a very natural definition, which Arit covered in her talks. And actually something that's interesting that I'll note is when we did this proof, we had to pick something that was in this set, which in topology terms mean that you have non-trivial cohomology. And actually, if you're a full co-boundary expander or boundary expander, you'll always have trivial homology. So you actually, the stronger version of this theorem actually will not work to prove SOS lower bounds. You need to have this small set version of the result, which is sort of interesting. Yeah, this should be less than or equal to alpha times m. Okay. Yeah, unfortunately, I'm out of time. So I'll just say like 1 minute, how in the world do you construct these objects? It turned out that most of the hard work was already done for us by coding theorists and by previous people in the HDX community. It turns out that these breakthrough works on quantum LDPC codes constructed chain complexes that looked like this, which had a slightly weaker guarantee. They had sort of this distance. I probably erased it at this point, but they had this thing that I called cosystolic distance, which was when this minimum was greater than or equal to alpha m, and they had it in both directions. And basically, what you need to prove for this result is to sort of upgrade. Cosystolic distance is sort of like having no short cycles versus having boundary expansion, and you just sort of need to upgrade their proof from no short cycles to having this relevant notion of high-dimensional expansion. And the way that it's done is you construct this high-dimensional object via what are called the left-right Cayley complexes. I won't go too much into it, but somehow you like put some squares in the middle, and you put some codes on the squares, and these define maps in both directions, and you place some objects on the squares that are robustly testable or like have co-boundary expansion in some sense. And then you use spectral expansion of sort of the global object to lift this robust testability to small set co-boundary expansion of everything. Okay, I think I'm out of time at this point, so I'll finish. Yeah, thanks.
Any questions for Max?
Okay, so yeah, I guess I have the following question. So let's say you take the neighborhood of one of the vertices on the rightmost partition. So that gives you like an even cover inside the XOR instance. Okay.
If you're in a chain complex.
If you're in a chain complex,
Yeah.
I guess you're saying that these, if you add up the clauses in these even covers on the variable side, you're going to get 0.
Yeah.
How do you know that on the target function side, like whatever you set as the right-hand side free clause, that also gives you 0?
Oh, I mean,
I guess it's
right. Sorry, I think I maybe failed to say this. When we do this like subspace thing, we're always gonna, when we actually do the SOS bound, we're always gonna pick beta that's in Z1 without. Which way do I write the? We can use linear algebra to pick something that's a cocycle that's not a cobound. Yeah, I think I forgot to say that. So to get the lower bound to work, you need to pick something that is a cocycle.
Oh, I see. And because it's in the neighborhood of one of these vertices, it actually, like the parity checks make it fall inside like Z1.
Z1 exactly better than satisfied.
Yeah,
Okay.
That's the definition of the
Yeah, sounds good.
I think.
Is there a, do you think that there's fruitful?
I don't know. 2 XOR should be easy, right? So is there
To like over.
I don't know. Can you do this with like reductions in the hierarchy? I'm not sure how you would do this directly. I mean, okay, I'm lying in that like already this actually doesn't give you a 3 XOR instance. It gives you like maybe like 100 XOR instance, because we don't have like degree 3 versions of these high dimensional expanders. So already I have to sort of do some reduction within the hierarchy to get to 3 XOR. I don't know if you could do, I mean, I'm not really an expert at that. If you could do some sort of PCP reduction to do this.
Like to 2x, like 2x, like unique games. That's what you're saying.
That's what you mean? Yeah.
So of course it's hard.
Yeah. Right. Okay. Yeah. Sure.
Yeah.
Any more questions?
Yes. Imperfect.
Yeah. I mean, okay, here you have like the equivalent. So it's not,
Yeah.
Okay, so let's thank Max again. So we have a reception now, I believe, and otherwise we'll see you next.